So today we are going to see about structured concurrency and Project Loom. So Project Loom is one of the new, I would say, the most important changes coming to JDK. Maybe modules was bigger. Actually, it was not actually a user-facing one, and it's kind of one of the biggest changes which is coming to the JDK period. It's going to affect radically how we choose our frameworks and how we program, and also it's going to make Java even faster compared to, and stop people moving from other to other languages. And I would say like what are the real problems which we face, and then like how Project Loom helps. So this is actually going to be the overview, and moving to the next level. This is actually a safe harbor statement, like what Oracle does actually. But again, this is information only, and it's nothing to do with my company, and I just work for it. Okay, so that is something just to add. So as you can see, the Duke has its own has threads all around itself. So it's going to be completely threading based. And I'll start with the concept of Little's law. So the Little's law is kind of, again, a throwback. It's 1960s stuff. And then I'll move to the constraints of what we have as a request per thread model, which we generally use in our general servlet based, or like most of the Java based frameworks like Tomcat and other stuff uses the servlet interface. And then what are the advantages of having the request per thread model? And moving to asynchronously, what are the benefits and what are the pitfalls in that? I'll go through the need for structured concurrency, define it, what is it all about, and then how Java is going to try to implement it, and then how Project Loom, which is the actual virtual thread implementation inside the VM and the core libraries, and how we're going to all get together and increase the performance and write a maintainable, scalable code in Java. So that's the goal. That's the way this presentation is going to flow. And let me start with Little's law. So Little's law is actually a queuing theory law, which was actually built in, which is actually theorized in the 1950s. So it's actually, you can imagine Little's law in a context of a bank. Okay, so like, so if you take the L is the number of counters in the banks, which if you go to a bank, you have bank tellers, and you have, it's the number of counters there. And lambda is the incoming number of people which are coming to queue. And W is the mean time in which a counter can able to service a customer. So the Little's law states that like L should be equal to lambda into W, which means that like the rate of incoming customers into the multiplied by the mean time which is required for servicing the customer is the number of counters you require. So this is actually this is proven after a lot of mathematical calculations in the late 50s, but again, this law holds good for actually imagining a server. So if you actually imagine a server, what happens is like it has a number of incoming requests, which is the actual lambda. Mean time for the request to get service, which is once you get the do get or do post in your servlet API, in your servlet framework of any choice of framework like a Tomcat or anything, which will actually take your request and then process it. It's going to take some latency for processing it and then replying back. So, so this is the mean latency, and L is the number of threads or the concurrent requests which could be handled by the server. So these three values govern the capacity of any machine. So if you have a lot of incoming requests and then your mean latency is higher, then you should start scaling up your system to more servers because your capacity will be breached. So what are the factors which actually influences L? So L is the important value here, right? So there are.
Sorry to interrupt you. Could you go into presentation mode? Sorry to interrupt.
Do you want the entire screen? Because okay,
yeah. If you're comfortable with that.
I think so. There is a problem. You are able to see everything because like.
Yeah, no. I think there's a problem. Yeah, it's kind of going in two screens.
Yeah. I think I have an issue with this keynote. If it's okay, I can continue.
Okay, then let's leave it. Leave it as it is. Yeah, just leave it as. Sorry to interrupt. Yeah.
I brought it in. I should have put it in PPT. Yeah. Okay.
No problem. Sorry.
Let's go to this. So let's more look at the concept of L. What are the factors which can affect the capacity? So first one, like the number of TCP connections, right? Like any TCP, any OS should be able to handle TCP connections, and which is the basic IO. So when you move to like asynchronous IO, like NIO based servers also, what it efficiently does is that it actually implements the IO layer more better, while actually that is the interface between your actual service request. So that improves certain amount of performance. But again, you are actually going and hitting up a thread wall. So which is your thread pool of the actual service. So the thread pool T, which is the number of threads which your server can handle or the VM can handle, is the limiting factor for the major limiting factor for L. And then and also the threads in Java right now are completely linked to the kernel threads. So which means the amount of OS threads the OS can actually spawn, and then the VM can handle will be the limiting factor for your commit for your capacity of the server end. So, and also the other important thing is, like, let's say our request depends on multiple APIs which are connecting to the external world and then combining results and then getting it out. So which means if there is a thread T is blocking, so it has a lot of IO operations behind its interface, then what happens is, right, the individual threads, the mean latency time is also getting high. So what you end up is that if you are having a high mean latency, which is the W, and then if you have a lot, if you're constrained by the number of T which you can increase in your system, then you are ended up with unresponsiveness. So what we generally do, we just span a new server, you say Kubernetes, like you have auto scaling configured in your Kubernetes, and then you increase your number of servers which we have. That's how we simply solve this problem. But again, actually the Java and the VM is not exploiting the entire capacity of the capabilities of the OS, and that's one of the limiting factors what Project Loom is trying to address. We'll we'll go later actually. And also one of the important thing what we take for granted in request per thread is the ease of programming. Okay, so it's just the ease of programming what we have in do get or do post. It constructs some list of operations, and then it moves in a sequential way, which is an imperative way. Each step one by one, and then you completely finish the request, and then you serve the response back. So it's quite straightforward, clean imperative coding, which is easy to maintain, easy to organize, easy to test. So, but one of the problems, as I said before, like it uses the hardware badly. So there is no parallel computation, and then you are limited by the number of T you can create. So which means either you have to parallelize a lot of stuff within a system to increase the W, which is the latency part. Either you try that, or you have to live with the bad performance we have. And so what this is actually important, because like the reason why Node.js exists is because of this. So Ryan Dahl, as you know, is the inventor of Node.js. So he woke up one day and then ran a performance test on Tomcat, and he was so pissed off by the performance what it gave. And then he went to build Node.js, which is a non-blocking code. So whatever the imperative way gives you a blocking way of code, which is imperative, which is step by step, easy to code, easy to test, but again, it's bad for the hardware because it's not going to scale. And that's the main motivation for people to move away from imperative frameworks to reactive, or like different frameworks implement the asynchronous frameworks implement things differently. But again, that's the root reason for people to move out of imperative programming, because the performance is just not good. So, and asynchronous frameworks, actually, asynchronous frameworks are wide. Like there are a lot of frameworks. I don't want to go into the details of each and every one. But again, they can be. So, one second, I'll just have some water. So, what asynchronous frameworks does is that it defines a list of tasks, and each step can be executed in different point of times. Okay, so that's the core concept of any asynchronous framework. And then you publish to some place, and then somebody else will pick up another task, and then it will execute. So it is good for the hardware because you're not blocking your main thread, and it's gonna scale good. But the most problem is it's too hard to reason code. So anybody who has written a lot of asynchronous programming will come to a conclusion. It's good in theory, but again, if you want to build really big products and projects and maintain a lot of code base, it's going to be hard to maintain that code, hard to reason that code, and hard to profile. And it throws out a very effective abstraction of imperative programming, which has been built for decades. And I'll emphasize that the abstraction of imperative programming is not so straightforward, because we write imperative programming because we are born with imperative in the imperative world, and we have written that way, so we take it for granted. But again, there are some very effective abstraction which which are critical to write scalable, maintainable, to write code which could scale in the quantity, because we write, if you build any important products or like or services or like backend, so you're dealing with a lot amount of code, and it has to be organized and it has to be tested properly. Then if it's some random like few lines of code which is going to execute somewhere, that's okay. But if you're maintaining a real product and real backend services, it's going to take a lot of code, and organization and effective management also becomes a very important thing. So let's start to move away from request per thread model. Okay, so before that, I'll give you a small example. This is kind of a classic imperative blocking code which we write. Imagine that there is a financial institution which is using this code. It has 3 tasks right now. So I'm going to place a deposit. It's going to compute my exchange rate, and it's going to add some interest. Because I'm going to place a foreign currency deposit. So imagine that I'm going to place a foreign currency deposit. So I have Singapore dollars. So first it has to convert to USD, and then it has to add interest. It has to subtract the charges, whatever the handling charges, and it has to give it the result. So you can see there is a clean step-by-step approach. And if you look at this code, that we have this, and imagine these 3 things are like get the current exchange rate, the current federal fund rates are all APIs. Okay, so it's going to call some APIs. It's not going to be a direct method call inside the JVM, and it's going to call some remote functions like an API to actually compute. So actually, if you look at it, so and if some servlet thread is going to access this part, and the breakpoint is here. Okay, so imagine that there is single thread servlet has actually has the request, and then right now it has to give the response. So what it does, it's going to wait for all these 3 operations to finish, which can take a long time, which can slow things stuff, but it's going to be easy. So this is easy to code. It is straightforward, and maybe I'll give you, so maybe we'll just run this code. Okay, so I just had coded this before. It is imperative blocking, right? So okay, the maturity amount. So so I'm going to paste around like $100 of money, and then see what is my maturity amount. Is 69.3. Don't worry. So like the exchange rate is 0.7, so you get $70. But again, the interest rates are 0 right now everywhere in the world, maybe except for India. But again, so the interest rates are completely 0. So I'm going to get less money whatever I invested. So that is the state of deposits right now. But again, as you can see, like if it executes in a sequential way, it's very intuitive. But again, it's slow. So that's one of the problems of having imperative and a blocking code. But it's actually very easy to code. But let's try to move away from this and see what else we could do rather than worry about this performance issue. So let's try to code this in a different way. So imagine that we have this place deposit. So the main method, so the main thread or the server thread is going to access this. And then we are going to do as a multi-stage computation. So the output of the first stage will be going into the second stage, and the second stage output will go into the third stage. So if you are so let's imagine that if your execution of the first stage is correct, we're gonna pass to the second stage. If it's wrong, then you're going to just log the error and then stop. And at the end of the thing, we are going to publish to some random queue or a random framework, which is going to receive my request and then do some other response to the intended client. Okay, so but this code actually will scale a lot, because you're just going to remove your main thread from your, you're going to unblock your main thread. And then imagine this compute method executes in a different threads, and then it's going to combine everything, and then it's going to publish to a different queue. So this will be fast. But again, maintaining this code, again, it looks like Node.js, and it will be hard. And let's try to make this more simpler, maybe not more as complex as that, but still maintain our asynchronous flow. Okay, so we'll go to a concept of monads. So monads, I think so. I'll give you a brief introduction of monads, and then we'll see how JDK implements monads. Actually, as you see, a pure function is a subroutine which takes an input and then throws you an exception. So this is a clear example for a pure function. It takes an input, gives you an output. If there is some issue, it's going to throw you an exception. Okay, so that's the classic example for a subroutine or a normal function. But monads gives you superpower. Okay, so monads take a value and a mapper class and a mapper function. It maps the value, it applies the value to the mapper function, and then wraps the result and then gets it out. So it's kind of complex. Maybe I'll show you with an example. So if you look at a flat map, it's a classic case for people who use flat map in JDK. It's a classic case for a monad. It takes a value, applies a value, and then wraps the value inside a stream and then return back. Optional.flatCom is there, and then completable futures also have a compose function, which is which is a monad. So monadic types can really help you wrap the value and then do this kind of asynchronous work. So let's go to a more tamed version of the non-blocking code which we saw earlier, and then you can see this compute value right now is so the compute. So if you can see the compute function here, each and every function is right now is going to execute in its own thread. You are giving a supply async here, supply async. It's just completable future that supply async here, and everything. So it's going to return the value wrapped up in a monadic function, which is again the completable future here acts as a monadic function here. And then you can use the then compose feature of completable future and compose all these values. So what happens is the first operation executes in a separate threads. Once it finishes, it's going to send to the second operations, and once that is finished, go to the third operation. And finally, when you get the result out, you either print it if you get an error, because the when complete will pass will actually take the exceptions from the earlier stages. And then if there is an error, you can print the error, or again you can publish to a random place where it's going to respond to. And again, this will be completely non-blocking. The thread which is accessing it will just exit immediately, and then all the operations will be executed in a different thread, and then it's going to function as normal. Let's try to run this code also. Let me see where I have non-blocking thing. So so I just added a sleep method here so that we are blocking the main thread till it's complete. So it's again the same thing. You're executing executing each and every API. So you're going calling the currency conversion, federal funds API, calculator, and then finally you're sending to a random queue with the value of 69. The same computation is happening, but everything is in separate threads. Everything is, and the main thread will execute unless we are actually holding it. It's going to execute. So it's completely asynchronous. Yeah. So, and actually, can you even simplify this? Take the old method and then use the completable future that supply async, and then apply async. So all these things also going to almost do the same thing. It's again taking the output of the first stage, supplying to the input, and then doing it in a completely non-blocking way. So again at this stage again we are losing still the ability to throw exceptions, which is very important, and ability to have a return type. So we don't have a return type of this function, so it's going to publish to some. You need some frameworks help to actually get back the result in some other place of the code. So mostly, if you look at any production like very high load code, we implement mostly in forms of queues, which will submit to some queues, and then slowly it will go and execute each and every task in the queue. Finally, you get the result out of it. So it's not going to. So that's something we do, and you can mute. I'm muting Gagan. Okay. So yeah. So monads becoming harmful. So let's imagine that we want to have a return type. So till here we can't have a return type because we need to do everything in async, but we can still have a return type in the form of a monadic return type. So it's still not going to be calling the actual join here. It's not going to block the main thread, but still you're going to get the value out of it, and it's still completely asynchronous. But here, what it happens, right? You are actually polluting the entire call stack, with what the place deposit will be called. So let's say a method which is calling this place deposit, it is again going to be a completable future, and so you're going to pollute the entire call stack with completable future. And it's not very desirable, and you can't write a raw production maintainable code where completable features are everywhere. So these monads have their place, but it should not be exploited to have it as return types for methods, which is going to exploit the entire call chain which it calls. Okay, so it's so that's the problem. So as you can see right now, we are trying to move to an asynchronous world, but again, we are having roadblocks in the form of easy organizing of code. And this is the same roadblock actually people faced in the 60s, but in a different way. We'll go to that actually right now. So again, throw back to 60s. Structured programming was invented in the 60s actually. Before it was all go-to statements. So we take everything for granted right now because we are completely grown up in a structured programming world. So C was structured and all C++, Java, everything was structured code. So as you can see, there is a sequential way of executing code here. So you have blocks, if-else blocks. If-else block has to close. So you can't branch away from if-else block. It has to have an else, and then code has to flow, come back. And then let's say there is a loop also. You have to exit the loop. So there is some either you exit in a break or you completely close the loop, and then you have to exit the loop. And also in the function call, right? The function call has to return some value, or it has to pass back the control back. So it cannot keep the control and then keep moving on. So that's an important abstraction which was built. And before it was all go-to statements, and it can achieve the same thing in go-to also. But these abstractions were built to simplify stuff. And these are the so if you look at the papers in behind it, so this notes on structured programming was written by Dijkstra itself. So he was his main concern was actually abstraction. He wanted to write programs which you can actually hold up in your place, and you don't need to really think about it. So let's say imagine that we have a system.out.println. So if system.out.println, you don't need to really worry about how would the internal implementation of system.out.println. It's not going to the internal structure is not. You can treat it as a black box, and it's going to return back your control once you execute it. So it's not going to say that I'm going to put it into some framework or a queue, and you listen to that framework to get your actual value, what has been printed. So once you say system.out.println, it prints and exits. So that's an important abstraction because we take this abstraction for granted. Once we move away from this abstraction, all these problems which have been discussed earlier comes. So also his concern was actually on induction for scaling things. Scaling things here is actually means that if you are writing a big product or a big project or a lot of amount of code, you can write this thing properly for a small place, maybe in a small environment or like in a test. But if you're making this part of a programming paradigm to an entire product or a big backend project, it's not going to scale. It's going to create it's going to create a lot of issues. So that's the induction he had. You can't induce that you wrote one block correctly and then say I'm going to write everything properly. So that's the induction he was very concerned on. And he said like go-to was a destroyer of abstraction. And sequence. So when one deviates from the sequential flow, it seriously becomes hard to reason your code, and building a large project will become even difficult. So, okay. So unstructured in the 60s was like this. So you have a go-to label, and then from a go-to label, the control flow switches to somewhere else. But in the new world right now, we have unstructured programming in the forms of completable future.run async, executed at submit, where you just take the program flow, submit to a different thread, and then just don't worry about it. You're just giving away control of your execution stack. And then the epitome of it is Go, which is actually has a language keyword built into it as Go, which is very similar to GoTo, right? So Go functions are actually very analogous to GoTo statements because it doesn't let the control flow comes back to your flow. It's going to be executing in a set. You can manage this again. You can use channels and other stuff. There are other stuff, and also you can manage the completable future also in a different ways. You can manage it, but again, there is no built-in language structure which stops you from doing it. That's an important constraint. So structured concurrency is again a new concept. Actually, it's you can take a look at a block. So there is a Python framework called Trio, which actually implemented the structured concurrency first in Python, and that's an inspiration for even JDK to build this actually. So what structured concurrency mandates is that when you branch as 2 or 3 threads which are running in parallel, you have to mandatorily join it before you exit. So there is a mandate for joining or cancellation. Let's say this task 1 takes a lot of time. You cancel the entire block and then move it, rather than actually hoping that somebody else will actually capture the result and give you back. So this gives you subroutine safety. Yeah. So that's one other reason. So this ensures subroutine output. So, and also it opens some things like automatic resource cleanup. So that I'll discuss later. So yeah. it makes testing far easier. So when you can test this method, so comparatively easier than any other complex things which we discuss later. So, and also the goodness of imperative abstractions are there. So because most of the important software right now, take for granted, are being built not by asynchronous framework, but by imperative way. So that's the most of the important software which we use right now. So let's see what Project Looms actually does in this context. So again, Project Loom addresses two steps. One is increasing the number of the little's laws, right? So the little's law, we come back to the little's law, increasing the number of L which VM can create, and how to organize your threads. So two things actually Project Looms actually addresses. So again, when you look at java.util.lang.thread, right, it's a 24-year-old idea. So actually threads, the biggest problem with threads is threads actually maps to OS thread directly. So when you create a thread, you are actually invoking a kernel thread. And when the problem with OS threads are, right, OS threads are designed very generically. It's gonna be you can grow a thread memory stack, but you can't shrink it back. And ultimately, what is actually a thread in Java terms is just a stack which can block. But OS threads does far more than what Java requires. And also one of the things is it's very coarse, and it's been designed for variety of tasks. It's not only designed for only a small number of minute IO tasks which we need to fire out and then get it back. It's not going to it's been designed for coarse grain of things which are going to run in OS. So, and also in general, what we do is we don't create threads. We stop creating threads after Java 5. We have outsourced it to create by Executor service, which will actually create the threads, manage it, bound it, and then queue it, do all sorts of complicated code to help you not to blow the memory out, and then it will execute safely. But again, you're constrained by the number of threads which you can actually, or a task which which you can create inside the Executor service. That's the real constraint which we have, but it's far better managed than actually you creating your own thread. So what are virtual threads? So virtual threads are threads which can completely be handled independently in the VM itself. It's a very lightweight. Virtual threads can be multiplex. So like one carrier thread can actually hold multiple amount of virtual threads. And again, virtual threads gives the main important things what we require. It can be suspended, it can be resumed, and you can actually wait, block, and everything. And the stack can block. So that's the most important thing. And you can create millions of virtual threads before you run out of memory. So that's one of the most important VM level as well as the core library level changes which is happening in Project Loom. And I don't want to get into the detail of how it's actually implemented in the VM. So because there is a way how the stack is walked, and then how the stack is saved, and then how the stack frames are get it back, because maybe that's more complicated, and I want to keep it as an overview and a developer point of view here, and what would be the implication for the developer here. So the unit of virtual thread is a continuation. So continuation is kind of I can run the code for this. It will be more informative. So continuation takes a scope and it takes a runnable. Okay, so this is a scope and and it takes a runnable here. And you start running this continuation, right? So let me try to run it. Okay, so it says before, okay, and then first time I'm calling the continuation.run, it will execute up to here, and then there is a call to yield. So it will give back the control. So once, and then what you can say again another time run, and it will start from here. So the code will start from here only. So as you can see, it prints before, and you check for is done, it's false, and then it prints again after, and then it's done. So this again simulates the complete working of your thread stack. Implementation wise, it does a lot of stuff in the VM which we don't want to get in now. And also one other thing is that you can call this yield in any depth of the stack. So you can have very complicated code inside this, and then you can yield from any depth inside the call stack. You can yield, and this is the unit behind which the virtual thread will actually execute. So if you go back to the Prezo, so what is a virtual thread? Virtual thread is actually a continuation and a scheduler. So its continuation is the basic unit of concurrency which is going to be built, and then the virtual thread is going to help you in the scheduling with the scheduler, which will run on a normal kernel thread. So you are multiplexing a lot of virtual threads inside one scheduled executor. So once inside one scheduler, and that's going to manage all your virtual threads inside a real kernel thread. Okay, so the real kernel thread will be the backing, but again you can block the stack, unblock everything inside the JVM itself. So if you don't need to go to one level down to actually block. So the evidence is here. Okay, so this is a very famous. I don't know if you look inside the JDK, right? So there's a method called park and unpark. This happens within the lock support class. So whenever you use any one of your concurrency frameworks and you say reentrant lock.lock or reentrant lock.unlock, so it finally gets to this place called path. Okay, so it goes through the lot of call stack, and finally the call stack ends here. So here, if the virtual threads, if it's a virtual thread, then it will be yielded actually. So your execution will just suspend here. It will call the virtual threads at park. But if it's a normal thread, it will go into the actual kernel thread and block the kernel thread. So that's how the change inside the JDK is actually happened to support this kind of virtual thread. So virtual threads can be created in any number. You can check. You don't need to worry about any memory issues when you create virtual threads. So let's go to the structured concurrency. Let's now go to the structured concurrency part. So like when I was discussing before, like structured concurrency mandates you to actually close the block or join the threads before you proceed. So that's the mandate of structured concurrency. Let's run some unstructured concurrency. So it's a very simple code. So you have a thread pool executor here, and then I'm going to submit two tasks, task 1 and task 2, and then I'm going to say end structure, and I'm going to call the executor shutdown later. So when I run this code, yeah, so it's working properly. It should not work. The end structure should now it's works. So there should be some uncertainty here. So the end structure is called before the task is completed, because we don't mandate any structure in this code. Okay, so anything which could only when shutdown anyway, everything has to close down. But before the shutdown is called, you are not mandated to exit out of this block. So it acts as a classic non-structured concurrency. So, but let's move to a structured concurrency world. So before we move there, I'll just explain. So now we have a new thread pool. So we use fixed thread pool. This is going to create real threads, but you have a virtual thread pool also now. So that is actually added in the project Loom. And again, I'm to explain, like I'm using Java. This is actually a build which is available right now. Project Loom is actually, you don't need to build it before we need to build this code. So there is builds are available directly from the OpenJDK site. You can download and you can play with this. It's already available, and it's built based on Java 15 actually. So all the Java 15 features will be there. And one of the things is, so the new virtual thread executor, and we are supplying with the deadline here. So deadline is like I'm just placing at 10 seconds right now. So this virtual thread pool can create n number of threads. And also one of the important things what you see is, right, generally when we create executor, we create somewhere in the global world and then try to reuse it. So we don't create thread pools inside small method blocks, because the fear of having to wake up and shut down big OS threads. Okay, so generally we don't do it. So because virtual threads are cheap, you can create it and destroy it in very cheaply compared to actually creating a OS thread. You don't need to actually share this variable. You can actually have a scope here. And then one of the important thing here, you can see a try release block. So if you're implemented files in Java 7 plus, you should know about the try release block. So now executors implement the auto closable. So once you exit this block, now is the mandate of joining. Okay, so this is the actual structured concurrency block here. So this is a structured concurrency block. So here you have a task 1 and task 2. These two can execute in parallel, but once you exit this block, you need to ensure that the entire execution flow control flow is back to the main thread, and then everything is closed out here. So that's the mandate. So the mandate is now supplied by threads which could be easily created and destroyed. So the resource creation and the resource deletion is also handled very efficiently compared to what we had before, where we used to share resources. And also the important thing of deadline, right? So once we start this try block, if any one of the tasks is taking a long time, let's say 10 seconds plus, then the entire thing is cancelled and then you throws an exception or transfers back the control. So that also an important thing. Let's say one task is an IO task, it's going to query one server and then it's going to wait for till infinity. That's not going to happen here also. So it gives you subroutine. So this structured concurrency block gives you a subroutine safety right now compared to what you have before. So let me try to run this. Let me show you an example. So here you have start structure, start task 1, task 2, and then you got to have end structure. So the structure is ended here, and then the transfer, the control transfer is out here. And so now it's completely a normal imperative programming, but we still have been executing all these two things in 2 different threads. So we are doing the same. But let's move again back to the preso. So again, I'll give you another example also. So this is actually a completable future. So I'm going to supply a lot of async tasks. And then inside the completable future, I can send this executor service itself. So that is an API and run async. If you go to run async, it can take an executor also. So, and let me try to run this one actually, so you can see the differences. Here what I've done, I've just created the same virtual thread pool, and then I'm putting inside the try release block, which is the structured concurrency block. And then I'm going to run this. So here you can see all these things are executing in parallel, but again, my structure is started here and it's ended here, and everything is joined before we exit this block of code. Everything is joined, and then you are getting the result output. So that's an important change what we have from before. So this mandates you to do it and gives you a simple way of creating and destroying things. That's also an important thing. So let's now get back to the preso. Yeah. Now let's rewrite the same code what we have before for the place deposit in structured concurrency world. Okay, so again, instead of actually creating we fixed thread pools, we can create now virtual thread pools and then supply everything into its own thread. So the main thread can actually wait till here, and you can actually delegate all the responses to us to different thread pools, which can be more efficient. So in this case, like if we are still in the old world, let's imagine that we are still working in an old Tomcat, and then we want to place all our other IO requests in a different thread pool. We don't want to make sure that our own thread pool gets blocked. You can actually transfer the execution to a new virtual thread pool and then compose all these functions here, and then you call the join, and you're going to get the output. The same, now it gives you subroutine safety. Each and every one is going to execute in its own thread, in its own supply async. Compose everything using the same monadic return type, but you join it before you send it back. Okay, you join it, you send it. You're calling inside a try release block. This executor will be destroyed after this block ends. So you don't keep your executors away. You keep on having the executors. So let me try to run this also. So now we are implementing the same code, but it is in a structured concurrency way. So I'm getting the same output. It is supplying each is taking one stage output to a different stage. Everything is executing in its own thread, and it's completely freed up your main server threads. Okay, so that's one important change which we do. But again, let's say Tomcat is upgraded to using virtual threads itself, right? Like then the old code, you don't need to change even the old code. So that itself will have its performance. You can have blocking imperative code, but again, the cost of creating threads is going to be so cheap. You can continue with this code rather than actually changing anything. Okay, so we are here, right? Okay, so we are here. So again, this is not a great example for actually exploiting parallelism, because if we have a framework which actually supports the virtual threads, the old code itself will be doing good. You don't need to change anything. And again, one of the things you can see a pattern here is that you are doing accumulating values. So this is a classic accumulator pattern, but there is a requirement here because the second stage, it doesn't have any meaning before you go to. So before I compute compute my exchange rate, I need to finish this block before I go here. So it's an accumulator. It's a built-in data flow dependency which is built into the needs of my program. So, but there are cases in which we mistakenly do it. So that I'll give you an example. Okay. So it's a very simple code. It's a hapless code, but again, this 2 runs very, very differently. Okay, so it's a very simple code where I accumulate the value of sum. So I'm going to calculate the sum of all 100 numbers. So I'm going to have var sum, and I'm going to compute sum equal to sum plus I, and then return sum. But these two codes execute in a radically different way. Why? Because this accumulates the value. And one of the important problem I'm missing is that the sub problems are not dependent on each other. For this computation of sum, I can compute 1 plus 2 and then 99 plus 100 in 2 different threads and then add it together in the final. It's not going to make any change in my code. So typically, any classic examples of divide and conquer algorithms can actually can be completely parallelized. And examples of dynamic programming, like let's say you have a dynamic programming problem, where the second output will be depend on the first output's result. It's not going to scale. It's not, you cannot parallelize it, but you can parallelize all divide and conquer problems. So this is a classic example where you can actually decompose the problem, provided if you're splitting and your recompositions are cheaper. I'll come to that actually. So how this thing executes in the real world is that if you have this accumulator, right? So first I have my sum value is 0, and then it will be 1, and then 1 plus 2 is 3. 3 plus 3 is 6, and then finally get the output. But if I run this code runs in a very different way. So this can actually execute in all in different cores actually. You can execute in different cores. So 1 plus 2 can be done, 2 plus 3 can be done. All these two could be combined together, and then finally I'll get the output. Provided if I don't need, the sum actually doesn't depends on the pattern in which I accumulate. So I don't need any ordering in that. So there is a lot of cases in this code we overlook this kind of exploitable parallelism, and we just use the classic accumulator pattern. But if there is data flow dependency, you have to do. But if there is no data flow dependency, you can easily parallelize it. And how we could now see an example of how we can use your new structured concurrency to parallelize stuff. Okay, so this is a classic example. Okay, so what we have, sometimes we need to actually download in parallel. Because certain use cases, because what my product does is, right, we actually run a crawler. So my product actually scans the web for vulnerabilities in source code. Okay, so we have to download millions and millions of URLs to figure out is there any mention about a CVE data or something like that. So it's kind of a real use case, and a lot of the cases will have. And this is kind of an example I'm taking. We are going to download these two things in parallel, and now we can say you can use it structured concurrency to it. So let me go to the source code itself. It will be more easy looking at the IDE. So download parallel. Okay. So here what I have is I create again a virtual thread pool, and I supply this virtual thread pool to an HTTP client. I think so. I think people are using this HTTP client too. This is released in Java 11. It's kind of far better than any other Apache clients which are there. And what I do is right now I pass this executor into a structured concurrency block, and I supply all these URLs. So we have these URLs. And I supply all these URLs to a send async. So send async will actually send you a completable future, and then I'm going to accumulate all these completable futures in tasks. Okay, so all this thing, what it does branches everything, so it comes to the same problem, same diagram which I showed here. So this is going to parallelize my download. So each and every URL is going to come parallelly download, and then it's going to join, and then it's going to execute. So what I do is, like, when I handle the response, also here I can do complicated things. I'm just returning the body without doing anything, but I could do parsing. I can do a lot of I can do some regex analysis, which is required, or I can do some even ML stuff also if I want to do something cool. Okay, so that's something we could do, and everything, all this handle response, everything executes in parallel, and you just accumulate the results finally before you exit out of this loop. So again, it gives you subroutine safety, but I'm able to exploit parallelism where I don't have an accumulation of data flow dependency. So these things, everything can be downloaded in parallel, everything can be processed in parallel. So I don't have a data flow dependency, and I can create n number of threads which I want, which is with the new virtual thread pool, and this is going to scale. This is going to scale logarithmically compared to linearly. So let's imagine we are not submitting this and then you're going to do it in linearly. The linear time and logarithmic time, you can see how it will divert after the n keeps n is subsequent substantially bigger, then it's going to deviate a lot. So that's the and you can do this safely. So this is it's going to almost end of my presentation. So what Project Loom gives you is the ability to create a lot of threads at will, and also structured concurrency mandates you to use this thread in a responsible way, and then close it, and then go back, maintaining subroutine safety, and you can throw an exception, test it properly, and then write scalable large amount of code. So, and maintainable large amount of code. So currently, I'll just want to walk through the limitations of this. So limitations right now, I'm not sure about the current implementation. Maybe I'm not following it. This is a status maybe a few months back or 3-4 months back. It doesn't work well right now with synchronized blocks, so you have to use a reentrant lock. I'll show you an example for locks also here. So here is a classic locks. You have a shared state here, and I'm going to create again in virtual thread pool here. I'm going to create a reentrant lock, and I'm going to lock here and then unlock so that the shared state get properly updated after the in this code block. So as you can see right now, this both shared state gets updated properly, and then final state right now is task 2. Task 2 is the final state right now. So all these things gets the locks work properly here, and then you can do but the problem here is that you can't use synchronized block. Still you can use only reentrant lock here. I'm not sure whether this is implemented right now, and you can't do a wait and notify doesn't work inside the synchronized block right now. So it will actually block the carrier thread rather than the virtual thread. So why it will not work inside a synchronized block if you are having and it will block the carrier thread. So it doesn't work properly now, but I'm not sure how the support is right now. And continuation right now doesn't work on native. So if you're calling any inside this continuation block, if you're calling any native code, it's not going to work. So make sure that all this code which is calling inside this is Java code, so it doesn't work with JNI right now. And Java.util.concurrent requires a lot of tuning, because again the executive service was completely built on the thought that you should not create threads, and threads are very expensive, and then so you block or unblock the thread as late as possible. But right now it doesn't require that way, because we can block and unblock in a cheaper way, and you can create and destroy threads in a very cheaper sense compared to what we have earlier. So that is the important difference that virtual threads have brought. And so there are a lot of tuning which requires to make sure that we are calling in a virtual thread context. It's been more efficient. So that's the current state, I guess. But I'm not sure about the real current status right now. I'm not following a lot in Loom dev. Maybe the Java guys might have a better understanding and when it's going to get released. But it's going to be a substantial, very important release, and it's definitely this release. It's available right now in OpenJDK.java.net, and it's quite working. And you can even try production programs, test it out, like whether it works properly with your with the existing code you have. And right now it doesn't work with Gradle, I guess. So maybe it should work, but there are some limitations with Gradle and other stuff. So these are the references. There's a lot of YouTube videos also. Ron Plessner is one of the developers here. He has given some exciting, very insights into this, and a lot of insights into it. And you can go to YouTube and search about Ron Plessner, and you can actually look at this notes on structured concurrency. Very important block. The Python library called Trio has actually implemented this. An important, so you can have production code. And there is Kotlin implementation of coroutines also. You can take a look at coroutines. Coroutines again doesn't use the virtual thread concept, but again it mandates the structured concurrency construct. So coroutines is something you can take a look. But again, the problem with coroutines is that you have to annotate a method called suspend and resume and other stuff at the front itself, and it doesn't allow you to call the yield from very depth stack. So its integration is far more difficult to compare to what if this get released the integration complexity is far lesser here. And there is a big blog by Ron Pressler in cr.openjdk.net, so you can take a look at that. And yeah, that's it. So any questions? Maybe I've been there's a lot to take, or like any questions?
Yeah, Shrinath, there's a question from Sanjay. He's referring to I believe he's referring to Kotlin routines called as coroutine, and then Go routine and virtual threads. So the question is it the same concept, but the implementation or underlying implementation is different? And The follow-up was also, would Kotlin need coroutine after virtual threads? Will they drop it or replace internal working?
Yeah. So the internal working of Kotlin, see, I'll give from Go routines, right? Go routines has a very similar concept of virtual threads. It against the conceptually, it's everything is same, because even Go routines will not create heavyweight threads. It's going to create a very lightweight thread, and that's one of the real selling points of Golang. Golang, people wants to code in Golang because it's not going to create heavyweight threads, and you can create a lot of threads, and the code will scale. So that's one of the real selling points of actual why people move to Golang. And again, you can manage these coroutines with some channels and other stuff. There are a lot of libraries in Go which you can manage. And the other important thing for coroutines in Kotlin, right? Coroutines in Kotlin will anyway implement a virtual thread once it's released. But again, I'm not sure about the how usage, or it will be for kind of it will accompany what Java does, but in a different way, because Kotlin does the same thing. It mostly implements the same thing, but it gives you a different way. If you look at records also, right now, records are kind of, Kotlin also has its own kind of record type struct, which is built before. And Java also has, so it can be a choice. And also Kotlin, you can integrate Java and Kotlin so well to each other. That's one of the things. And the suspend and resume function of Kotlin, right, it's partly inspired from async IO from .NET. Okay, so the inspiration is more different compared to the way that the structured concurrency mandates. Okay, but again, both can live together, and both will live together. There might be implementation changes inside Kotlin. So that's how I see its roadmap. But again, Kotlin, once Project Loom releases, only Kotlin can build anything over it. So that's kind of, anyway, this is also changing a lot actually. So that will be a work in progress in the future only. I'm not sure how it's going to, but again, there will be something, a complementary, which Kotlin will build what Java also has. That's how their product roadmap is. Yeah.
Hello.
Yep.
I have a question. When you are using threads, so how you ensure your threads are efficient? Like in terms of every computer has different type of CPUs. Like the cores are arranged in a different way. So if you are using threads, like how you ensure when you are running a parallel, doing some parallel programming or running parallel threads, it is using all the threads efficiently. Like some processor, they just switch the threads, and some processor, they run the threads parallelly. How you ensure that you are using all the cores of a hardware efficiently from Java?
So, I'll come back to that. Okay, so the point about so again, so when you look at threads, right? So you have to look at from an OS point of view also. So the most of the things, how a thread behaves is handled by the operating system itself. Okay, so the kernel will create a thread, and then it will create a stack, and then how it manages, that's mostly dependent on how the OS is written in the first place. Okay, so if you look at in the JVM point of view, again, JVM maps to a OS thread, and if let's say there is a multiple CPUs, if you want to run a parallel sort, typically what it does, it creates a common scheduler pool, like a 4-chain common pool or something, which will directly map to a kernel thread, and then the kernel thread will manage how to use the CPU or IO. So it's not in the control of JVM itself. Okay, so that's one thing. And also an important thing is, right, the whole concept of moving away from kernel threads is that the usage of threads from Java context is mostly to have a stack which can block, which can suspend and resume, and that is more important than actually doing a parallel computation point of view. So that is the reason for virtual threads actually you use. If you want to do, let's say, a parallel sort, it's better to use direct normal threads, which will actually map to a kernel thread, which will decide that mostly it will go to a CPU, which will schedule in different CPUs and then aggregate the results and get it back. So that's how it's you have to separate the concerns actually. So virtual threads, mostly you should use it in the context of IO related work, and normal heavyweight threads should be used in a normal compute bound task. So typically when we move to a instream.parallel, right? So instream.parallel internally uses a 4-chain common pool. 4-chain common pool only has 8 threads. Okay, so it only takes the number. It's not 8 threads. It depends on the number of CPUs you have. Let's say you have like 5 CPUs, like the virtual CPUs I'm saying, which again includes the cores, and then it will have only 5. So it's not going to take more than, and then it makes sure that this schedules with an kernel, which will actually schedules in the core, in the CPU itself. So, but you don't need a lot of number of threads when you do compute bound work. The most of the number of threads which we require is for IO bound stuff, and IO bound stuffs also what we do is our requirement of thread is to just block, but do something else and then come back. So that's the requirement of a virtual thread.
We have a few more questions from the audience. The first question from Rajesh, it is that similar to the channels, is there anything in Golang's Go threads?
Similar to channels, is there anything?
In Golang's Go threads, that's what is the question. Do you have anything similar to channels? Okay, I think he's referring to, sorry Rajesh, please clarify.
Yeah, the question is like the Golang has a channel, right? By default, a communication mechanism.
Yeah.
So is there something similar?
So yeah. So the structured concurrency mandates against Go channels actually. So again, channels are again your asynchronous framework. So if you look at what is a channel is, right? Okay, you can abstract to sending messages to somewhere else and then receiving to and doing something else. Okay, so you're communicating through a channel, right? You're sending, oh, I'm finishing my thread, you take from me, and then you do something else. So this is again classic asynchronous programming. So which is again what the structured concurrency wants to move away from. So you have subroutine safety. You don't need any special channels to actually communicate what I'm doing and what somebody else is doing, and you make sure that your creation of threads are cheaper. That's it.
Okay. Another question from Raja, and which I think Sanjay is also interested in, is that when you're writing concurrent, now we are using say reactor code or concurrency code, one of the challenges programmers face is that how do they debug such code? Because your code is branching at different levels on say if we use Project Loom, it's on virtual threads. How do you analyze or debug such code? If any observations or any ideas are there on that?
The logical point, you can't debug so easily your asynchronous code. So asynchronous code is hard to debug. I think everybody would understand. But again, you can debug easily here because maybe I tried to debug something. Okay, so let's try to debug. Let's say if I want to have a breakpoint here, right? Like I don't want say something else. Okay. No, maybe I'll just run the subject concurrency CF. Okay, so here if you look at executors, I don't know how do I really, but anyway, this all will be gone completely. But one of the important thing is, right, like you can actually I'll try to run a breakpoint here actually. So just yeah. So one other thing is, right, here you have a start structure, and then this will be one of the 10 threads which will get blocked. Okay, so all the 9 threads would have been completed right now. Okay, so it's, maybe the x equal to 1 will be blocked right now. Okay, so let me see. I think right now the x should be task 1 should be the last. Let me see if I'm able to do that. Is the first, maybe I blocked it differently. Okay, so that's the point, right? One of the things is, right, it's always hard to debug concurrent code. But again, each and every thread will be having its own breakpoint, so it'll be harder to debug. But one of the good points is that if you reduce this block of concurrent code, right, you can debug here to actually collect what is the result. So instead of actually debugging through each and every block of concurrent code, so you can have the smaller blocks, create more threads, execute all these things, collect the values, and then see, oh, what's happening in my data structure. So that is the easier point to debug instead of actually having separate transfer. And you can never debug asynchronous code. I don't know whether you've been successful in debugging it.
Okay. I hope that answers your question, Raja and Sanjay.
Adding to the Srini, that the point is very correct. So if the concurrency code is being taken by the VM rather than taken by the user, the debugging itself will become easier, right? So you just have to believe that underlying VM architecture or JVM is working fine. That is someone have to believe that. and then like how Srini showed, like say the accumulator pattern or something like that, right? So if the code has been reduced on the user side, the debugging will become much easier. What do you say, Srini?
Yeah, that's what. So if you reduce this try block, right, like, and make sure that, let's say this is a system.out.println is tested, okay, so, or you are writing some important code here, okay, and make sure that you say, make sure that you test this block properly. A similar example is like compute, okay, so the compute is going through different threads and different, but you can write a small test so that you make sure this compute works properly, okay, and then you can test whether get std works properly, but and you can test this entire block properly, in the sense, because it's going to converge everything. This try block is going to converge. If it's not going to converge, then it's going to be testing. Okay, so that's how you debug and test easily, because you are decomposing bigger blocks of code into smaller blocks, which could be easily testable, and then you are only taking the concurrency part to a smaller blocks where it joins and gets you the result back, rather than waiting for some message to come back. So if, let's say, I want to debug let's you non-blocking team, right? Like, I can only test whether this method is called, and also I need to say I have to wait for the threads to do some time unit at sleep to actually. So this is very unreliable testing. If you want to do this, it's a very unreliable. So actually, we do this actually in our normal real production code, especially when you use with queues. People who have experience with using with SQS or like RMQ or in that world. So typically, when you say, oh, whether it's published, that's the test you can do. You can't do anything else. So that's an important change actually, because that gives you this code with structured concurrency can be tested far easier, can be far safer compared to testing this code. I don't think so. You can only assume this testing because it's really not testable. That's the whole point of this, having complete asynchronous blocks in our code. Yeah.
Okay, thank you. Okay, this is a question which I also wanted to ask. It's come from Sanjay, that what is the, how relevant are reactive frameworks like RX Java and Project Reactor once Project Looms becomes, what is a general availability, and how will these reactive frameworks still be relevant?
So, from my perspective, there's no relevance. But again, it depends, because people, when they get stuck with the frameworks, it's very hard to see. Hibernate is something which people are not able to remove. Okay, there are other frameworks like Speedment, or like other framework like JOOQ. I don't know somebody who used that. But again, these are all far simpler. They are written for Java 8, and they're far cleaner. But still, people use Hibernate everywhere. So it's reflective. It's hard to maintain. It's just magic behind. But see, again, the frameworks are always sticky, in the sense like frameworks, if they stick, they're hard to remove. Okay, but again, it will be a war only. But ultimately, it depends. Like if you look at module system was not able to win the war. So people still use class path only. Nobody's using module path. So most of the people, production running code still uses class path. But again, in this feature, people will be more convinced to move to Project Loom, because if they have existing structured code, they don't need to change anything. They don't need to change every to Reactor. So people who are already in Reactor, maybe they have invested a lot of money, but they might be slow to move. But when they start new projects, they might be really tempted to move to Project Loom, because it's something built in inside the language. You don't need to have any external frameworks to actually do anything on this. So that is something important. But again, for Project Loom, from a user perspective, it's far easier. It's not the case for module system. Module system still, it's not integrates well in a lot of places, but it has. But we use model system in JLink and other stuff. It's very useful in real production environment, because we ship in our company, we ship an entire agent, which is around 20 MB with the JVM itself, because we can't it's used in a CI environment. So CI environment might have Java or not, but so we ship the JVM along with the agent, which runs in CI pipeline. But we have to reduce the dependencies of other things, so that we ship a small VM. Otherwise, it will take like 400 500 MB to download Java itself, right? So there are use cases in which model system was used, but I think it's a better use case for Loom, because people who are already there in the imperative world will easily jump ship. So there is not a lot of changes which we need to do. And mostly this will also be an under the hood. I think mostly Tomcat will go ahead and implement this. So if you look at it, right, it will not come to even the developer level. Tomcat will go ahead and implement virtual threads, and then you're not going to see it, because NIO is something developers are not really using it. But again, NIO is implemented in Netty and other stuff, and you can see real performance difference in that with using a normal blocking IO. So something will go on like that also. So that is the future I see. But reactive frameworks will be there, but again, it's going to be, I don't see the use. It's going to be again the war of programming methodologies. Okay, so there was a big war by Donald Knuth also. Knuth was actually saying you are not using GoTo properly. You just don't you know to use GoTo properly, but you can still program in GoTo, and that's going to be an argument in any programming paradigm. Okay, so if somebody if people are in if some languages choose structured concurrency as the path to move forward, there will be some other languages like Go which will not choose structured concurrency as the path move forward. So this will be exist, compete, and then see who will. And that's so it's always the case, right? People start with Ruby on Rails, and then finally, if they want to do, if their company makes money, then they will start writing in Java. So that's the way the world will go. That's what I feel.
Okay. Just it's a question from my end, Srinivas. See, I remember there was a question from one of the previous audience that structured concurrency is against the use of channels for communication, right? So, can you elaborate a bit on that? Why it is channels are considered to be, probably non-performant, or what do you say? When I kind of moving away from the paradigm of structured concurrency. Can you just elaborate a bit on that?
That's what. So
The reason I'm getting into the question is, hello.
Yeah.
Yeah, the reason I'm getting into the question is that there are a lot of reactive frameworks which use this concept of not exactly channels, but like, for example, Vertex has a concept of event bus, or some people use Zookeeper for these kind of communications, or they even go to the extent of using messaging queuing architecture like say Kafka or anything else. So I'll just to elaborate on that aspect a bit, if you could.
Yeah, I would elaborate. So because even my product uses elaborate messaging things to do things. So what are the, see, again, there is going to be arguments and against this model or not. Okay, so again, the way to get best performance is actually unblocking. Okay, so unblocking your code, and that's what Go Channels does. Everything, all your different types of event bus, or like any reactive frameworks, everything goes on in a virtual concept of publisher subscriber. You publish, I have done something to somewhere, and then it will go and take the message and do some other task, execute task B sometime later. So that's going to be, or it will communicate more information other than this. So it's going to become you can fit all this programming, all these frameworks into this paradigm. Okay, so this paradigm will continue. It's not going to end. But again, this is if you're in the structured world, this is going to be better compared to moving to your asynchronous world. So asynchronous world, people generally move it for getting more performance. But right now, you can get the performance with your with the ordinary JVM you already have with writing structured code. That's the major movement of structured concurrency and Project Loom. And also the most important thing is, right, you don't need to throw away your abstractions. So why do you want to complicate your coding? Why do you want to write complex coding when you can write it simple? So that's also another argument. So if you want to, if somebody has maintained an event bus or like any of their asynchronous framework, they know the difficulty in writing tests and then maintaining it in the long run. Okay, so simple. And also messaging system will exist because of my code, what it does, it's actually crossed the entire world, entire internet for finding out vulnerabilities. Okay, but I can't run all this thing in a web server, because web servers have only 200 threads. It's gonna die. So I have to queue it in some messaging system, which will keep on go and crawling the internet to get things out. So there are use cases in which where you can use messaging system, where you can use you can use what do you say, asynchronous framework like publisher and subscriber. But again, you don't need to complicate simple parts of the code. That's the whole point of this concept. So you write a proper web service which has predictable subroutines, predictable results. And if let's say you're not able to scale to with 300,000, 200,000 threads also, because let's say I want to download a million URL. Definitely I can't parallelize million URLs maybe it will be too hard to a JVM. Then you can go and add maybe Kafka MQ or Kafka or whatever MQ, your favorite MQ, and then queue the request, and then slowly take maybe 10,000 at a time or 20,000 at a time or 30,000 at a time, and then download. But again, the queues will be cleared off far faster. You're going to have far responsive thing compared to what you have in the older world, which if you do it sequentially. Sequential code really is slow, and you have to exploit parallelism when you can, and do it in a safer way. And that's the whole point of project.
Okay, can I add just one aspect to here? So at the moment, with reactive programming, you can have intra-application programming happening with use of reactive programming paradigms. Like within the application, you're communicating using an event bus.
Yeah.
But now with Project Loom coming in, intra-application programming can be left as it is,
Yes.
using the structured concurrency concepts. But inter-application communication, where two applications are communicating within themselves, there can still be use cases of using React publication subscription communication models. So
Yes.
is that probably a way of summarizing it?
Yeah, that's the thing I was talking in my previous statement. So let's say even the intra application programming itself is so overwhelming. You can still use publisher subscriber model. Okay, so let's say in the sense of a message queue, right? Let's say I have millions of URLs to download. I don't have the capacity, and I don't want to scale up my server. At that point, I could use a message system to queue, let's say, and maybe download 50,000 at one point of time. Okay, and that could be faster. I could clear the queues faster. And for inter application, definitely you should use for any, you can use your queues definitely wherever is possible. But let's say your server itself is so performing, then you can just call the API directly. Okay, so if the server is not really performing, then you can send messages so that it will process and then reply you back later.
Probably this is not a relevant question, but in publishing subscription, you have this concept of at the guaranteed delivery mechanisms.
Yeah.
Now, obviously, they come in only because we are talking about the pub sub communication model. They will obviously not come into either structured concurrency or all those things. But I think it's not relevant. Is it a relevant aspect here? Because in case of structured program.
So those are all independent concepts. The publisher subscriber will be there, SQS will be there, RMQs will be there, and everything will be there. But their usage for having scalability will change. That's what I'm saying. You can scale far farther with your normal JVM compared to having this infrastructure, okay, in the first place. And then if you want to scale more, then you can put the infrastructure. That's another point. Okay, let's say I want to scale. See, simply one of my tasks which I do is, right, I crawl the entire GitHub of around like 1 lakh repos, and then download all the commits. Okay, all the commits which have been done in the last 10 in the last 1 day, and then I have to implement a machine learning model over that, and then to see whether there is any vulnerability present in that, and then I have to aggregate the output. So we have to crawl the entire 50 or 1 lakh repos. You can't scale it with normal structured concurrency, but you can use it with a combination of structured concurrency. Maybe download maybe 15 repos in parallel, and then execute all your things in parallel. But you still queue your 1 lakh repos which needs to be downloaded. Okay, so that both can be used in parallel. But the point is, right, you can scale up your existing code far farther than what you imagine, because you still see in SQS it just gives you 10 threads for reading messages. Okay, so it's so non-performing. If somebody has integrated SQS into their code and then maintain why my consumer is not scaling, then you have to just see that it's going to only have like 10 or 15 threads to actually implement to read your message. Let's say I want to consume like millions of messages at some point of time. SQS is not going to even help you. You have to transfer your execution stack to a different thread pool and then do some complicated stuff in that. Okay, but again, these are all could change. So the SQS message queues can have like millions of threads right now, and then because it's just doing an IO one. So at the framework level, you can see a lot of changes, and then which will percolate down to your programming nodes.
Yeah. Okay. Thanks a lot. Okay. There's another question from Vinayak. I'll come to Rajesh's question after that. He said in the blogs related to Project Loom, they mentioned fibers. And are these the same as virtual thread construct, or do they refer to continuation unit?
Yeah, if you looked at I just gave this presentation like 2 months back somewhere locally here, my company. I was mentioning as fiber. Even the class name was fiber before. Okay, so the naming convention has quite changing because it's kind of work in progress. So if you look at the virtual, I'll just virtual thread. Yeah. So if you look at like 3-4 months back, this was actually fiber extends threads. Okay, so this both are referring to the same, and the naming is, I think this will be the name for the future, because it was initially named as fibers. Now it is virtual thread, and this name will stick around because it's almost it's close to completion, I guess, if I'm correct. So the both are referring to the same.
Okay, great. Thank you. Okay, coming to Rajesh's question. His question is a bit of a difficult one. Is like, any performance benchmarks are available for comparing the performance of Java virtual threads versus Golang Go routines?
Yeah, maybe we could start a GitHub project and then contribute. But I've not seen something like but there is, if you look at, there are benchmarks which to compare a normal server and a server which uses virtual threads. I think there should be somewhere up. Maybe I'll try to find the link if I could find out, or we could write it. It's not a big thing. Somebody could from this community can help me write some Go channels, and then we could write. We have OpenJMH, and we could see what the performance of both.
So yeah, that's the question so far. Any other question? Yeah, sorry.
Srini, how is the changes on the tool side like JStack or JMC? I mean, they have adopted the changes of the Loom.
I don't have idea. You are JDK Intel guys.
No, I mean,
No,
have you ran JStack, and is it providing you any details about the virtual threads or something like that?
it should be able to provide virtual threads, but I have not tried it actually, to be honest.
You have not tried it. Okay. Thanks, Srini. And Srini, I have a request from you that I think it's good to have a session on future and completable future. I mean, it's very much related, and I know that you already have that in your archive.
Yeah. So yeah, you say like it's good to have a.
It's good to have a session on completable future.
That's already there. It's 4 years back. I could do the same thing. Yeah.
Yeah, I know that. I know that.
Yeah. Maybe that's what I said. I just jumped into completable future, hoping that people will know about it.
Yeah, I can understand from your PPT that you expect people to know completable future, but I think most of the people know. But it's good to have a session on that. So Vic, what you say?
Yeah, I definitely agree with that, Vaibhav. And since she didn't have to do a lot of hard work of preparing just to come and talk.
Yeah.
So I would say that I would definitely, I'll probably get in touch with him and based on his availability, schedule something. And we have Praveen seconding it also, that yes, a session on completable future would be much appreciated.
Sure.
Okay, there's another question from Sanjay. Okay, sorry, Srini, please go ahead.
Yeah, actually, completable futures is very relevant. Actually, I could give you some real life production code examples also, like what use cases it might be really useful also. Yeah, I could go further on that. Yeah.
This one is a bit on a different note, but it's an observation from Sanjay that he mentioned that there are many libraries for managing Go routines. If you have any preferred library of choice, anything which you prefer or favorite, and he feels that the problem with Golang is that there are too many libraries and they're not quite standardized.
Yeah, that's a problem. Again, I work in a company which just scans libraries. Okay, so we crawl through the entire world about libraries. Okay, so library stability in Golang is always difficult, and it's even more harder in Node.js. Node.js is a complete hell. Okay, so that's a different problem. But again, I don't have any recommendations for channels library. To be honest, I have not really went very deeply into how channels work actually. So I'm sorry about that. I don't have a recommendation for that. What library you need to use.
Okay, this is interesting question. She's like, have you come across any kind of a comparative, article or blog on virtual threads versus the actors in Akka, or basically the actor pattern? because actors are also considered as lightweight threads
Yeah.
in Akka.
I've not come across that, but again, see again the programming paradigm is the bigger change actually. So if you look at nodes on structured concurrency, right, like that to give you a big comparison between all other frameworks. You can paint all other frameworks in one angle and then put structured concurrency in a different angle. Okay, so both are completely different, and that will give you the base in which why the thesis comes here actually. And for virtual threads also, right? See. You can manage the VM actually creates the threads actually if you look at it, right? Like so if unless the VM construct of virtual threads exists, which only exists after Project Loom, any lightweight is only a management of an existing thread. Okay, so you can create even executor manages our threads, but because we don't create threads, the executor is just a very complicated stuff for actually creating and managing threads. Lightweight, non-lightweight, everything again it depends on how the VM gives you any information. So the VM construct only will be built after Loom. And maybe the actors will also change. Maybe the internal implementation of actors will change, and coroutines will change, and a lot of things will change after the VM constructs are available.
Okay. Anything else from the audience? Anybody would like to share anything, ask anything specific?
I have a question. This one regarding the slide parallel task execution. Can you please go back to that slide and the code?
Okay, you want download parallel code? You want?
Yeah. So there you are combining like. Yeah.
Yeah.
So, okay, you are here like R is the response of all combined methods, right? If all combined tasks, right? R is the return.
Okay.
So, so it is the like suppose I am running 3 APIs and all the three APIs has different response. So, is it combine those all?
No, the point is that what is the color of the code? Okay, so download parallel. If let's say this is going to be a service. Okay, so some service API is going to call you, and then that will be one single thread, and one single thread will branch. Okay, so this will be the point. Like I'll show you. So this is I'm just giving as a main thread actually for thread 1, but the thread 2 can have a different branch. Okay, so that can create 3 more tasks also. Okay, so you can have like so let's say you have a server which has 10 threads, and then you're going to parallelize 3 at any point of time. Then you're actually downloading 30 things in parallel. Okay, so it's going to combine. Okay, so but this is a plain unit. So what you can see is that this is a plain unit in which is a unit of stoppage. Okay, so I have to join before I move out. But this itself can be called in inside a different thread, right? So that thread context is different. That's a main OS thread. So let's say you have 3 threads which are calling this to download in parallel, and 3 are OS threads. So that will be actually communicating with it. Will be each will be creating a new executor thread pool, and each will be executing in its own threads. So it's going to create 30 threads in your virtual world, and it's going to execute and then combine everything and give it to you. So that's how normal things work. Yeah.
Okay.
Multiplicative effect. So the point what I want to tell is you have a multiplicative effect. So let's say you are calling this itself in some other thread, you have a multiplicative effect. That's what I'm saying.
Okay. So, yeah, my question is that like that response is it like suppose here you are calling to URLs like Google and some another URL. Yeah. So the response is combination of Google and Edison URL, right? CNN URL.
And I think sorry to interrupt, Srini. I think what Abhijit is probably pointing towards is that a composition of responses is that
you can just collect this response here, right? So then apply if you want each and every time you get this response, and then you can just collect it somewhere. Like so here I just added a let me see how can I.
Oh, I got it.
Yeah, I mean it's a programming, it's a business requirement whether you want to compose a response or not, Abhijit. It's not something which the framework is doing for you.
Yeah, I got it. Now from code I got it. Like you can add it different responses.
Yeah.
Okay. Thank you for answering.
Anything else from anyone? Any other questions?
Yeah, hey, so I've read somewhere that virtual threads are based on user threads, and the which was actually in Java 1. Then it was replaced to OS threads, the kernel threads. So Srini, can you talk about like what exactly is user threads and what exactly is kernel threads? Any difference?
See, actually, if you look at the JVM itself, right? So each and every language, whenever you create a java.lang.thread, it will be actually mapped to a kernel thread. Okay, so that's how it will work. Okay, so each and every time when you create a thread, it's going to create a new kernel thread, and then it will transfer the execution and blocking of all the stacks, everything to the kernel. Okay, so you are not going to it's not going to work in the Java. Once you call this concept park dot what do you say? What's that code? Show you this one. This piece of code is important. Okay, so once you call this u.park, right, it's going to transfer the control to the OS. Okay, so this is going to be a low-level code, and then it will block the kernel thread, and then and everything will be transferred there. So that's how it's created. So it's a very low-level construct. Thread is a very low-level construct in JDK.
Okay, so but that's user level thread, right? The virtual threads.
Virtual threads will not even communicate with the OS at all. Okay, so virtual threads exist everything in the JVM itself. So it gives you the stack, everything blocking, everything does within the JVM itself. So it's not going to communicate with the OS at all. Actually. So there's no. That's what I said. You can't do native code. So the native frames will not work now in continuation, because this is a completely Java construct. So the stacks lives in Java, and it will be blocked in Java, and it will be closed in Java. Yeah. In the VM itself.
Okay, there was a question from Praveen, which is that in one of the slides, virtual thread is extending thread. I think you showed as a code example. So is this not going to be heavier and someone use it like a normal thread? His question is that since it's extending a thread class, what's the impact?
So the point is, right, when you extend the thread card, you can always override the implementation also, right? The implementation is completely override. Okay, so when you say sleep or wait, it's not going to go to a lower level construct and do it. So it's going to create everything in the JVM itself, and it's going to use the continuation as a scope. So, and again, when you create, so it's again a subclass, right? When you say thread t dot equal to new virtual thread, when you call, it's going to dynamically dispatch, right? It's kind of it's not going to actually create it's not going to create an actual OS thread. It's going to create a virtual thread.
Okay, Srini, was there in the URLs you have shared, is there any article which goes into bit detail about the difference between a virtual thread and a kernel thread? Because I think the question is coming quite frequently when people, I would say, probably prefer a more detailed learning experience.
So if you want to go very detailed, right? So you can go to this the last blog called CR at Open. The Ron Blesser is the actual implementer of this code. So you can actually go through this place, and he's given a very good example of how virtual threads works. So actually the plain example I'm keep on repeating, virtual threads lives inside the JVM itself. It has no communication with the OS at all. And when you create a java.lang, it actually communicates with the OS. So that's a major difference actually we need to take out.
Okay, two questions, which is when I see in terms of the trade-off, I think you've already covered the trade-off between virtual and native threads. I think it has been discussed quite extensively, which you just iterated right now, just a previous sentence. This is an interesting question that once Project Loom becomes mainstream, would there be a possibility of whenever you call thread T as say kind of defaulting to virtual threads, or it's probably we leave it to the programmers choice?
So typically what I said, right, like you will have a choice. Okay, so when you want to create a normal thread, so typically how right now people create threads, you're not going to create thread equal to new thread. You're going to create an executable. Okay, so there is a fixed thread. You can create a fixed thread pool executor, but that is actually create normal threads. Okay, and the option of having this virtual threads, this will create a virtual thread. So it says thread.build.virtual.factory. So it creates a virtual thread factory factory, and then it creates. And very simple implementation also. It just creates a new fiber. That's it. New virtual thread. So there is no big management of all how the thread pool executor works inside internally for a normal thread. So it's very simple implementation for a virtual thread, if you say. But this is how you have a choice. So let's say you want to do some very compute bound task, you better use a normal thread pool. And if you're using a properly an IO based stuff, lightweight, definitely use a virtual thread. It's not going to even create a OS thread, and it's not going to do multi-core programming. Okay, so if you create a virtual thread pool, don't do it's not going to use multiple cores. But if you create a normal thread, it will be using multiple cores.
Actually, I'm sorry, I didn't get the last part. You said don't do
multi-core programming. Let's say you want to do parallel sort with you want to do sum in parallel. I gave you an example before also, right? Sum in parallel. That executor should be a normal executor code, not a virtual thread code. But you can use it in combination. So you can typically, let's say I want to do download in parallel also, right? Download in parallel, this executor is better suited for actually doing your IO task. But let's say I want to do something. Let's say I want to pass the body and I do some sorting in parallel, right? That in that point, use a different executor. You don't need to use the same executor, right? You can use a different executor, which is based on a real thread, and you can use that. So that will actually map to OS thread, which will actually do a parallel computation for you.